Hello and welcome to all our fellow engineers. We are happy to be back in the studio once again, creating new content for you. We are starting a new series on pipe flow. So quickly before we jump into our introduction on pipe flow, we just want to take a quick moment to welcome everyone back. It's been about a year since we've really done any videos. And really that was due to myself as the studio head. We shut down the studio for about a year. I spent the last year at a new university with a brand new environmental engineering department. And it just really was so much work getting everything started and off the ground that I had to, really focus my attention on that for a year. But now we have all this, new content that I'd like to share with our engineering community. So we just want to thank all of our subscribers for their patience. I know it's been a while, but actually we thought we would lose some subscribers, but actually we've grown even bigger than ever. So we're really thankful for everyone who supported us. And so without further ado, let's take a look at the fundamentals of pipe flow. Okay, so here we are at the board, and we really wanted to start this series with the simplest, most straightforward example of pipe flow that we could really think of. And so what we have here is a single pipe, in between 2 points, point 1 and point 2, we just have a consistent diameter pipe with a flow going through. So we have a flow rate Q1 and a flow going out Q2. And then these what look like pipes sticking up are known as piezometers. And these are essentially, the greater the pressure, the higher the height of the fluid. So it's a way of measuring fluid pressure in terms of height of fluid. And so what we have here, you're going to have some component of elevation, right? And in this case, with a horizontal pipe, the elevation really is kind of arbitrary. So let's just say we have Z1, have a little trouble there, Z1 and Z2 at the center line of the pipe. Okay, so essentially 0 at point 1 and point 2. Then this height of the fluid is known as the pressure head. So we have P1 over the specific weight of the fluid. And that is going to give us a height that is going to be consistent with the height of this piezometer. And then we'll also, of course, have P2 over gamma. Of course, gamma depends on the fluid itself. And then if we connect these, we have what's known as the head grade. Okay, so that's our head grade line or head gradient. And this is essentially just the elevation plus the pressure head at each point along this pipe. And now it's important to know that these piezometers, they're right at the pipe wall. And so if you remember from fluid mechanics, the velocity at the pipe wall is what? It's 0, right? So there's no component of velocity in a piezometer. Now, if this were a pitot tube, where it would actually kind of dig into the flow of the pipe, that would actually give us a velocity, right? It would help, the velocity of the flow would push this up higher. And in that case, we would have here our velocity gradient. Okay, oops, sorry, I bumped the mic. And our velocity gradient is, of course, going to, let's see if I can draw this here. That's going to include our velocity. So V2 squared over 2G is going to be this height above the head gradient is our, really it's not usually called velocity gradient, sorry. It's actually typically called energy gradient. So this is your total amount of energy for the whole system, and you're going to have that on both sides. V1 squared over 2G is going to be this point here. So again, this is going to be in addition to the head grade that we have from the elevation and the pressure. Now, one last piece, and I apologize because these are all on top of each other here, but in this case, because we have consistent velocity, and we'll talk about that in a minute, but these energy gradient and head gradient are going to be parallel, right? And so it doesn't really matter which one you use, but the amount of loss of head is going to be, unsurprisingly, known as head loss, right? And that's this height here. And so this head loss is basically caused by the friction between the fluid and the pipe wall itself. And so the more velocity you have, or the rougher pipe you have, the more head loss you're going to have. So let's start putting some of this stuff together. Okay, so on one side, at point 1, we want to know the energy at point 1 relative to point 2, okay? And so what we have here, we have Z1 plus our pressure, P1 over gamma, plus our velocity, V1 squared over 2G, is going to be equal to our elevation at 2 plus our pressure at point 2 plus our velocity at point 2 plus what? Our head loss, right? That gets us all the way back to where we were to begin with. So these two sides are equal if we take into account each piece here. Now, there's two really fundamental, I guess, concepts of pipe flow that every hydraulic engineer just has to kind of come to terms with. One is going to be basically continuity of the flow. We'll talk about that in a second. And the other is just understanding essentially your boundary conditions, right? So in other words, if we look at this, we have to start understanding what we kind of intuitively know. For example, it should hopefully be obvious that in a horizontal pipe, the elevation doesn't matter, right? The elevation, whatever the elevation is at point 1, is going to be equal to the elevation at point 2, right? So we can cross these off. They're going to cancel each other out. Now, we know that the pressures are different, right? So that's one thing that we'll come back to. That's something we're obviously going to need. What about the velocities, okay? And this is one of these things that, again, you have to know this going in, or you really are not going to be able to solve these problems. So we know we have a flow rate, right, going through this pipe. What do we know about the flow rates 1 and 2? Okay, so hopefully you remember that the flow rate at point 1 is going to definitely be equal to the flow rate at point 2, right? Because we're going to assume that the pipe is rigid, so it's not going to like swell up and store more volume, right? And what's important about fluids when we talk about fluid mechanics, right? An ideal fluid is incompressible. We always consider them to be incompressible, which means it's not being compressed, so it's not storing any kind of volume in that way either. So you're always going to have the same flow rate. And if you have the flow rate, what's the velocity? The velocity is going to be equal to the flow rate divided by the cross-sectional area of the pipe. And if we have a single consistent area pipe, then V1 definitely equals V2, right? Because if A1 is equal to A2 and Q1 is equal to Q2, then V1 is equal to V2, right? So we know that we don't know what the velocity is, but we kind of don't care. We know it's equal between the two, so that's not contributing to any kind of change in our energy gradient. So essentially what we are left with is that P1 over the weight of the fluid, the specific weight, is equal to P2 plus head loss. Or we can say that head loss is equal to P1 minus P2 over gamma. So in this case, if we were to, maybe let's take some of, I got so much stuff on there I can't really get it off now. Let's maybe do like this. So if we were to say that this is, let's say, 6 foot above the Z1 elevation, and this is, let's say, 2 foot above Z2, then we know that our head loss in this case would be obviously 4 foot. We have 4 foot of head loss between points 1 and 2. Okay, so Obviously, in this very simple example, it really is pretty straightforward, and really couldn't be any easier. But they do obviously, of course, get much more complicated, especially when you start talking about pipe networks and parallel pipe flow and all kinds of other stuff that we'll be talking about. But again, so in summary, the most important thing, or the thing that you just got to be able to do, is look at a lot of different examples. We're going to definitely make some more examples, more videos with different kind of conditions. But you need to be able to say, well, we don't care about the elevation in this case. We don't care about the velocity, and now it's just head loss is equal to this change in pressure. Okay, as an example in this case. So I hope that was helpful. If you're interested in more on pipe flow, we're starting a whole new series, as we mentioned. We definitely would appreciate leaving a like. It helps us understand that this is something that people are interested in. But if not, either way, I hope this was helpful to you, and we hope to see you again soon. Thanks.